Yeah, so let's get started. And yeah, today we'll talk about some of the pending things from last discussion. And before we start, actually, there was some issue in the last recording. So my video was not recorded by the end. I don't know how it happened. I don't know really. I mean, maybe I forgot it to record, or maybe there was some technical glitch. No way to know because when I uploaded the video on the channel, then I realized, oh, it's only audio. But anyway, I have shared the notes with the NPTEL team, so you can, if you are interested while listening to that audio or video, I mean video format in audio uh, content, you can follow the notes and you'll be able to relate to them. Okay, so basically we discussed about Moore circle and other things, etc. So yeah, so let's start. And today we'll discuss some things about stress strain curves. I mean, this is a old topic. Ideally, we should have covered this in the last class itself, but it was, you know, a lengthy discussion on Moore circle, etc. Anyway, so we'll today briefly cover it for some time. And then we'll talk about some failure theories. There are many of them, and professor has talked about some of them in the class, which are highly used, such as octahedral and sorry, not octahedral. This von Mises and Tresca theory, but there are some more, and these are mostly elastic deformation failure theory, or within elastic limits, how the failure occurs. But when you are doing some forming process or some other plastic deformation process, there there can be failure in your plastic region also. So then there are multiple theories, but two of them are usually discussed. First is again law Levi-Mises equations. They are for ideal plastic kind of substances. They don't consider elastic strain. Basically, they neglect elastic strain as compared to the plastic strain. And then you have Prandtl-Truice equation. And those things are already discussed, so we'll just briefly touch upon them, and maybe we'll talk about some this hot working, cold working towards the end of the class, and we'll close the class. That is the brief idea for today. So let's get started. Uh, so let's finish our discussion on this stress strain curves. Okay, so first of all, you know, one second. Yeah, so you know the formula for uh, true strain based on the engineering strain that was also discussed in the class previously. So we'll start from there, and you know, first we'll just see. Uh, okay, so let's just see the what are the types of stress strain curves. Okay, so firstly you have linear elastic curve, and it goes something like this. So you'll have your stress axis as y-axis, strain axis as your uh, this thing. What is it? The x-axis, and these are like engineering strengths. And then you'll have usually in these kind of materials, you'll have slight elastic deformation, and then there is a failure. Okay, so at this point, the material breaks or failure. and this is typically observed in brittle materials. Okay, linear elastic kind of behavior. Then second you have non-linear elastic. So here, it will be, as the name suggests, it is non-linear. And elastic means once you release the load, it will come back to its original shape. The material will come back to its original shape, and it will look something like this. So this can be one example of non-linear elastic curve. Okay. Then you have the material else here, something like this. Then you have linear elastic with plastic curve. Okay. Oh, I should have actually given the title first. No issues. So you'll have linear elastic plus plastic curve. So it will not fail after elastic deformation. It will undergo some plastic deformation also, and it will look something like this. So you'll have some linear deformation, and then you'll have some plastic deformation. So during plastic deformation, if there is no strain hardening or something like that, the stress required will be, same, and typically we consider it as yield stress, etc. Okay, but again, in case of our steel, mild steel especially, we see some strain hardening effects. So in that case, what happens? You'll have linear elastic deformation plus strain hardening. You'll have this strain hardening basically happens because of increase in the density as well as movement of the dislocations, and you'll see those things in your materials engineering class. But just keep in mind that the keyword which is dislocations. So you'll have some linear deformation like this, and after that also during your plastic deformation there will be some strain hardening, and the required stress more for the deformation. And then lastly you can consider some ideal cases which are called as perfectly plastic curve. Sometimes in competitive exams they typically try to confuse students by these words. Nothing else. There is no real material like this. So here basically what happens, you will not have any elastic deformation as long as you applied the load. Plastic deformation starts. In reality, something like very less elastic deformation case as compared to the plastic deformation, that can be considered as this kind of thing. And then have you rigid material. So this material does not undergo any deformation under application of any amount of stress. Again, an idealization, but you should know how to show its stress strain curve. And stress strain curve just looks like a, if you just can guess, it is just a straight line along your y-axis. Okay, and somewhere down here it will fail. So material will fail without any deformation. That usually doesn't happen, but okay, ideally you should know. So this is like the broad idea, but you should know some things about stress strain curve. For example, I'll just give you some definitions so that it may help you in your competitive exams, etc. One-liners can be easily framed from these kind of questions. So first of all, when you have elastic deformation, let's talk about materials, real materials like steel or aluminum or other kind of metals, not the brittle ones. So elastic kind of things, elastic plus plastic. So here you typically, in your elastic region, there are 3 points. First is your initial point, and again this is your engineering stress strain curve. Let's say you'll have starting point O, then you'll have point A, let's say here somewhere. So O to A is called as proportional limit, or sometimes they call it as elastic or linear limit also. Okay, and you're still in the uh, elastic region only, but this A to B part, it's a non-linear part. Okay, so Hooke's law is valid till your proportional limit or linear limit. Okay, so that is very famous MCQ question that is asked from this case, that Hooke's law is not valid till your elastic limit. Okay, so A to B is your non-linear elastic deformation. So if you stop the loading at point B, the material will eventually return to point A, so which is its original shape. So there will be no plastic deformation. So what happens, and this is till point B, it is called as elastic limit. So this is your elastic limit. So okay. Yeah, so this is called as elastic limit, point B. So O to B is elastic limit. And then, depending on type of material, you may see increase or decrease, something like that going forward. But this is also elastic range. But what happens for the ductile materials, you will never know whether you have reached your elastic limit or not. So what typically is done is, some sort of plastic deformation is introduced, very less, so that you'll know that you have reached elastic limit. So what they do, they slightly, maybe I'll use some another color after B, just to know that you have reached point B, because before B, if you stop at any point, you'll come back to your original O. So you'll not know that what is your elastic limit. So in reality, what happens? They, let's say this is your B dash point. So this is called as proof stress or proof limit. Okay, so that is typically 0.02 percentage, 0.2%. 0.2% offset. One second. Cold, so that's why. Otherwise, please bear with me. Yeah, so basically, that end point, elastic limit point, B is also called as yield point, and so 0.2% plastic strain. Okay, because now we 0.2% plastic strain. Okay. So This is a general value. It can be more or less, but this proof limit or proof stress is used for materials without distinct yielding points or yielding point, okay, such as aluminium. So if you just Google the stress strain curve for aluminium, you'll see that it does not have a distinct yield point. So in those cases, proof stress is defined to mark the limit or elastic limit, and after that we consider plastic deformation is starting. But in steels, etc., you have a clear distinction between plastic and elastic region. So therefore, proof stress is not that important in this case. So that is the main thing. Okay. So what will happen if you stop loading at B dash point? You will not return to the original O point. You will return somewhere, some point O dash. Okay. And this distance is nothing but 0.2%. So that's how sometimes they define it that time also, that type also. Okay, so this is proof stress. Very important concepts. These are like very famous questions in your MCQ type of exams. Then there is something called as resilience. Okay, so resilience is nothing but strain energy stored per unit volume, or not per unit volume, stored in a volume of the material under elastic limits. Okay, so till the point it is not plastically deforming, in that case, whatever energy that you can store, basically, how do you define this energy, etc., that is not the part of this course, but you can still think about it in terms of because when you apply some pressure somewhere or some tensile force on some area, you basically apply stress, and that stress is nothing but kind of a work done on that metal, and it will store that. So it is nothing but area under stress strain curve up to elastic limit. Okay, so this O to B area, that is called as resilience, and it is typically, if you just see, it is a triangle. If you assume, then the sigma y is your yield point, and area of triangle is half of that. So you can write this resilience as this, and then you can use Hooke's law, and you can write various various versions of this. Okay, and this is like a property of the material. Basically, this proof stress, etc., are also property of material. So you should understand that each material will have different things like that. Okay, and then there is something called as toughness. It is total strain energy stored in a given volume of material up to fracture. So basically, resilience is only till up to elastic limits, whereas toughness is whole area, total area under stress strain curve. Okay, so then those things are there, that uh, modulus of toughness is basically uh, total area divided by volume. Then there are other things such as creep, fatigue, endurance. Those things you'll learn in your SOM class, etc. But yeah, before moving on, I'll just discuss one thing about stress strain curve for mild steel, because that's important, and in many exams it is also asked. So yeah, the topic is stress strain curve for mild steel. So you'll have some elastic region like this, then slightly, oh, 1 second, you'll have something like this behavior, and then after a point it starts to increase, reaches some peak value, and at certain point, this is your fracture limit. This, this is your strain axis, this is your stress axis. This for mild steel, this fracture strain can be as high as 25 to 30%. Okay, so you can elongate it that much. Whereas this E point, which is called as ultimate tensile strength, this is your fracture point. Or sometimes it is called as fracture limit. Okay. And you'll have this. Okay, so this happens at about 10 to 12% of strain. This is engineering strain, okay, not true. So that also you keep in mind. And then you'll have this strain hardening region between D to E that starts typically after 4% of deformation. And there will be, let's say, some point C or something like that. So this will be up to like 0.12% of strain. Then we'll have C dash, some B, and A. So this is a typical uh, stress strain curve for mild steel. Okay, so now there are different regions here. So this D to E region, this is called as strain hardening region, and this region where this necking starts. So basically your cross-sectional area starts to deform. In this case, this is called as necking or post-ultimate or strain softening region. Okay, so there are multiple names for this. This region is called as yielding plateau. Okay, yielding plateau. And as I said, this, let's say this was your origin. So OA is your proportional limit. Okay, and this, what do you call, uh, D is your elastic limit. So OB is your elastic limit, and this C dash point is called as upper yielding point. C is called as lower yielding point, and then C2D is your what do you say, plateau, yielding plateau. Okay, so we study this because for mild steel that the strain can be very high, up to 25 to 30%. That is a big deal. Usually, not all materials can have that. And this fall from C dash to C, it happens due to you know uh, sudden movement of carbon atoms and dislocations. Okay, so you'll see about these terms more in your uh, SOM class or somewhere. But yeah, this is particular to mild steel. Okay, not all materials have these kind of C dash to C drop and then plateau curve, etc. Like aluminium. Okay, aluminium will not have this C dash, C and D points. From D directly you will go to E and then F. Yeah, so those things are different in case of mild steel. And in the yielding plateau, what happens? Your dislocations, etc. They are adjusting. They start moving and they start adjusting. So that is the reason where you don't need to increase your stress, tensile stress. But in your strain hardening region, what happens? The density of your dislocation starts to increase, and to overcome those dislocation movements, additional density of dislocation and their movements, you need harder or higher tensile stress. That's why in C2 D2E region, the sigma value must be higher. You need to apply more tensile stress to pull them apart, because of dislocation increasing their density as well as their movements are higher because of higher number. Okay, so basically you'll observe this C dash to C only in mild steel and not in other steels also. This is like particular thing for mild steel. And again you can do one simple comparison between mild steel, medium steel, high steel, alloy steel, all those steels, because only carbon percentage changes between uh, these different type of steels. So what you'll observe is you'll observe something like this. So you'll have different kind of steels if you plot. Oh, sorry. So these two will be like high carbon steel or alloy steel also if you want to call them. Then you'll have some something like this kind of medium carbon steel. And then we just saw about our this is your mild steel. Okay, so one thing that you should note is for all types of steels, Young's modulus is approximately same, because the initial slope of all the steels is more or less uh, same only, and this Young's modulus value varies between 192 to 10 gigapascal for steel. Okay, standard value you should remember. Okay, so this was about your uh, these things, stress strain curves for mild steel. You can look it up for aluminium also. Aluminium again, it will not have a distinct yielding point, so that's why proof stress is important in those kind of materials, because you will not observe this C dash to C drop and CD etc. in aluminium. Okay, maybe I'll just draw the aluminium curve itself, so you'll understand why it is different or why it is unique for mild steel, the things that we observe. So in aluminium you'll have certain elastic limit, and then it will be like this, and it will break somewhere. So it's a smooth thing, so you'll not have any distinct yield points. Okay. And you'll just see in some time that we use this yield stress, because so this point, whatever, if you want to call C dash or C or average of them as the yield stress, we use basically yield stress to find or define the failure of your component, because we, in case of elastic material or ductile materials, we say the material has failed when it reaches its elastic limit or yield stress. Okay, after that, since there is a plastic deformation, if it is a brittle material, it will immediately fail, and you'll not have any indications of anything. That's why brittle materials are not used in many places, especially where stresses can vary uh, significantly, or some things can happen like that. But in elastic materials also, all things are designed based on the yield stress. Usually, we don't go into the plastic. If you are designing some component, we don't want it to be, completely deformed or plastically deformed. In some cases, like processing, like forming, which involves rolling, forging, all kinds of things, there we want material to deform, because these are processing intermediate processing processes. But if you have a finished product, we don't want that to go into the plastic deformation region. So that's why if you are designing any last or final component, you usually take yielding stress as the designing criteria. And in case of aluminum, etc., since there is no significant or distinct yielding point, we take proof stress as the uh, criteria to set your failure limits. Okay, so that is the importance. So that in every now we'll see some failure theories. Yeah, there you'll see we define everything in terms of yield point or sigma y. Or maybe I should not write it sigma y, because you may get confused with the uh, y-axis stress. So this is your yield point. Let's say we'll denote it by sigma naught. I think in class also sigma naught was used. Let's see. Okay. Since this is unidirectional things, so but I think you get the idea that in case of mild steel, etc., you have a distinct yield point, whereas in case of aluminium and lower ductile materials, lower melting point materials, you don't have a distinct yield point, so you take proof stress as your limit, design limit. Okay, and then let's talk about some failure theories, because that was also discussed in the class. And for yeah, and before we move on, regarding this Morse circle, I think in the last class I accidentally mentioned that for 6 faces, 6 Morse circles will be there. Okay, but it's not correct. Because we consider like shear stress and all are same on pairwise. So basically, for a cube where you have 6 surfaces, you will have 3 Morse circle, not 6. I think in the last class when we discussed Morse circle, I accidentally mentioned it as 6 Morse circles, but that is incorrect. If you have 6 surface geometry, it will have 3 Morse circles. Okay, so please keep that in mind. And then let's talk about some failure theories, and we'll focus our discussion on 2D cases more, because they are used for showing that curve. Yeah, 1 second. Oh, 1 second. I'm just looking for my, yeah. Okay, so there are two types of theories of failures. One is called as elastic failure, when you consider only elastic deformation as a significant component before the failure. And then there is a failure in your plastic domain. So there are also many theories like that, but we usually don't study them extensively for competitive exams. Okay. But yeah, there are theories there also. So 1 second. Okay. Yeah, so there is something called as yield locus, etc. Yeah, so we'll discuss some theories under the elastic limits because they are important, as I said. Plastic deformation failure theories, two of them were just introduced in the class by professor, which were David Mises and Brandel Ruiz. So you can look it up if you are interested into more. But elastic ones are important. So let's discuss theories. Theory of failure. Okay. And let me just see in the last class which notation we adopted, so that will. Yeah. Oh, we adopted XXYY, right? So yeah, then it's fine. We'll denote yielding point by sigma y only, because sometimes this sigma naught that is used for uniaxial principle, tensile stress, etc. So let's denote yield point by sigma y. Okay. And let's start. So there are in class also professor discussed two, one Mises and Tresca, but there are more theories. So we'll discuss one by one. First is called as maximum principal stress theory, which is also called as Rankine theory. Okay. And according to this theory, uh, you know, as long as your maximum principal stress is less than the yield stress, there will be no failure. Okay. So this theory says for no failure, the criteria it gives is your maximal. Okay. Maximum principal stress. So you have sigma 1, sigma 2, sigma 3 as your maximal principal stresses, because you don't consider shear stresses on that planes. So this will be your thing, and it should be less than your yield point. So this theory says that if this is satisfied, you'll not have any failure. Or in reality, what happens? We generally consider some factor of safety. So this FOS is factor of safety. So you don't design for yield stress also, because you know there are some inhomogeneities, some material defects, etc. So to take that into account and to have a safe design, we usually consider factor of safety more than one. If it is a very critical application, we consider more or higher factor of safety like 2, 3, 5, like that. But this theory fails because, or before that, we plot its yield locus. Okay, so what this theory says is, you know, there is something called as yield locus. Okay, so I think this was discussed in the class also, but it's basically 2D plot. You assume plane stress condition, you neglect the third stress or third plane. You just consider a 2D case. So if you have a 2D case like this, and if this is your principal axis, sigma 1, sigma 2, and we know that if this limit is within your sigma y, so this will be your sigma y, this will be your minus sigma y, and similarly this will be your plus sigma y, and this will be your somewhat minus sigma y. So basically you'll have a yield locus which will be just a square, because anything that falls in this under this square, one second, yeah, if anything or your stress condition, your 2D stress condition, if it falls within this square, so this will be your safe, you know uh, no failure region. Whereas whenever if you cross this square, you will have failure according to your Rankine theory or maximum principal stress theory. But what is observed in the real life is that you know this is not always true, because in real life or in practical applications, it is observed that the material that you have, you know, uh, like the ductile materials that typically we use, they they fail in under shear conditions uh, well below your sigma y, which is your yielding stress. So they fail well below that limit. So what happens? It is observed that ductile materials fail below sigma y under shear conditions. So if you apply like shear stress, etc., even if you don't reach your sigma y at any point, still you fail. And typically this tau max is given as 0.57 sigma y. So this is the experimental value for ductile materials. On an average, it is observed that material failure will happen at like around 60% of its yield stress itself. So therefore, uh, this Rankine theory is not suitable for ductile materials, because ductile materials can undergo uh, tensile or compressive deformations as well as shear deformations. Okay, so therefore you cannot use it, because by this theory in pure shear, if you consider, why? Because in pure shear condition, in pure shear case, sigma 1 becomes tau, sigma 2 becomes minus tau, right? And by this theory, your as long as your tau is less than sigma y, no failure, right? But in reality, failure is observed at 60% of this limit itself. So therefore, this is not a good theory for ductile materials, but this theory is suitable for brittle materials. Okay, because typically we don't employ brittle materials in torsion, etc. Typically, they are compressive or mostly compressive, and as long as that compressive strength is less than the yield stress, brittle materials do tend to follow this theory correctly. Okay. Okay. 1 second. Yeah. So then you have next theory, which is called as a yeah. Basically, what I mean is in hydrostatic condition, the material is always in compression, from all sides. So there, you know, usually failure doesn't happen because of compression. It happens because of some other thing. Okay. Like if any tensile stress is developed, then it will develop or propagate, crack propagation will happen. So those kind of things. So anyway, let's move on to the second theory, which is called as maximum principal strains theory. So first is principal stress and or Rankine. Second one is maximum principal is it principal or okay. Yeah, so sometimes this is maximum principal stress or normal. Maybe I'll just highlight this first. Normal stress theory also sometimes it is called. Okay. Instead of principal, they can use normal. So here is the maximum principal or normal strain theory. Okay. This is called as I think Vincent. Saint Vincent. Yeah, Saint Venant. Sorry, Saint Venant theory. Venant's theory. So this theory says that like previous one, here if your normal strain or principal or strain in any direction is as long as it is less than the uh, yield strain, then it will be safe. So this theory says that for no failure, your maximum of your three principal strains should be less than the yield stress divided by Young's modulus. So this is your yield stress, yield strain, and sometimes it is divided by factor of safety and then divided by Young's modulus. So that is also there. So just take 2D case, because 3D cases already discussed in the class, but for some examples in 2D cases are very important for your competitive exams. So let's take your principal stress or strain as epsilon 1. It will be sigma 1 minus mu sigma 2 by E. Right? This is what we know from our previous class. And let's just check what happens in a pure shear condition. In pure shear, let's take sigma 1 is tau and sigma 2 is minus tau. Okay. So in that case, your epsilon 1 will be uh, tau into 1 plus mu by epsilon, right? And it has to be less than by sigma y by E. Let's say factor of safety is 1. Therefore, tau should be less than or equal to sigma y by 1 plus mu. Okay. So in general, for ductile materials, mu is 0.3. So therefore, this tau becomes less than or equal to 0.76 sigma y. So you can see here also it is over predicting, because from practical experiments it is observed that if the multiplier is 0.57, then it works, or less than that. So this theory also has a drawback that it cannot be used for uh, what do you say, ductile material. And in case of brittle material also, this is not good idea, because usually brittle materials are all compressive. They are not put under shear stress conditions usually. So therefore, this basically boils down to the better to use the first one, the Rankine condition. And here if you plot your epsilon 1 and epsilon 2 along, let's say, sigma 1 sigma 2 direction, so your yield locus for this Saint Venant's theory, it looks something like this. Let's say sigma 1 and sigma 2 like this, principal axis. So you'll have a rhombus kind of thing. One second. Yeah, it will look something like this. And this will be your sigma y minus sigma y minus sigma y. So you see, at some points your stresses can be greater than your yield stress. Okay, because this theory doesn't bother about your uh, maximum stress. It only cares about maximum uh, strain. So therefore, the yield locus is a rhombus. But this is not useful theory. And how it comes is basically, you consider that your epsilon 1 has to be less than plus minus sigma y by E. and epsilon 2 has to be less than plus minus sigma y by E. And epsilon 1 and epsilon 2 are, epsilon 1 is nothing but sigma 1 minus mu sigma 2 by E, and epsilon 2 is sigma 2 minus mu sigma 2 by sigma 1 by E. So because of, if you plug these values, and then you'll get equation of rhombus in terms of sigma. Okay. So then there is a third case, which is called as maximum shear stress theory, which is nothing but the von Mises theory. This is Tresca theory. Von Mises will be next. So this will be maximum shear stress theory. This is called as Tresca. Sometimes it is also called as J.J. Guest theory, but more commonly it is called as Tresca theory. So as the name suggests, this theory says that for no failure, the criteria it gives is your maximum shear stress should be less than or equal to your shear yield stress. Okay. And shear yield stress is basically your yield stress by 2. This is called as your shear yield stress. That will be half of your yield stress. Okay. So in other cases, if you are using factor of safety, sigma y divided by factor of safety by 2. Okay. So what happens here, if you consider this case, tau max has to be less than or equal to 0.5 sigma y. But we see from experiments that the materials will not fail even up to 0.57 sigma y. So therefore, this is called as conservative theory for ductile materials. Okay. And the one drawback is, it will say that you need more material. So therefore, high cost. Okay, so that is one disadvantage of using this. From safety point of view, it is good. Safety is better, but again, you are doing over conservatively designing, so therefore it will be bad from the economical perspective. Okay. And this theory, there is a glaring loophole here. What if all principal stresses are same? Okay, so note, if all principal stresses are same, in that case tau max becomes 0, because tau max is nothing but sigma 1 minus sigma 2 by 2. If sigma 1 is equal to sigma 2, then tau max is 0. So therefore, this Tresca theory is not applicable in such cases. Okay. And then yield locus, we have to plot the yield locus. So the thing is, yield locus in this case looks like a tilted hexagon, because the condition is tau max. So this sigma 1 minus sigma 2 by 2 should be less than sigma y by 2, right? This will be tau max in your plane 1, 2. So therefore, you have one condition which is sigma 1 minus sigma 2 by 2 less than sigma y. In another case, it will be sigma 1 minus sigma 3 by 2 less than sigma y by 2. So therefore this will be sigma 1 less than sigma y, because sigma 3 is 0 and sigma 2 less than sigma y. So this will happen in 2D case. Okay, so since we are interested in 2D part, okay, so this is on your sigma 1, sigma 2 axis. So let's say this is sigma 2 and this is sigma 1. Okay, so let's say this is your sigma y limits. Okay, so if you plot these three regions here, what you'll observe is that you'll get a shape like this. This is called as tilted okay, so this is also very important question as far as competitive exams are concerned. Okay, and then we have a okay, 1 second. Yeah, so basically you'll get a hexagon like this. In these two quadrants it will be straight lines, and then there will be square, okay, in the other two quadrants. Then you have a next theory which is called as maximum strain energy theory. Okay, strain energy theory. This is also called as Hayes and Beltrami theory. Not very famous name, but just for the sake of completeness. So for this theory gives the criteria that for no failure, your maximum strain energy per unit volume should be less than or equal to yield strain energy per unit volume. Okay, so what is say this maximum strain energy per unit volume should be less than or equal to yield strain energy per volume. This is also called as modulus of resilience, because just in this previous discussion we saw that resilience is nothing but area under the elastic limits, area under the sigma epsilon curve under elastic limits. So basically this is equating energies. So instead of stress and strains, we are equating energies. So sometimes this U symbol is used for strain energy, and it has to be less than your sigma square y square by 2e. Modulus of resilience is given by sigma y square by 2e. In some cases, if you have given a factor of safety in the question, you have to divide sigma y by that and use that. We typically assume sigma, what do you say, uh, for factor of safety 1 for plotting yield locus, etc. But in other questions it is fine. And this U, which is strain energy per unit volume, as I said, typically we take it as half into sigma into epsilon, because that is the area under the sigma epsilon curve. And since we are talking about maximum things, we take principal values. So in 2D, your U will be half of sigma 1 epsilon 1 sigma 2 epsilon 2, because we want maximum strain energy, right? And then you have sigma 1 as epsilon 1 minus mu into sigma 2 by E, and epsilon 2 as sigma 2 minus mu into sigma 1 by E. Okay, so those things we already know, so you have to plug those things in the in this formula, this epsilon 2 and epsilon 1, and then put it in this sigma y square by 2 equations. So what you'll observe is this becomes 1 by 2e sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 less than or equal to sigma y square by 2e. Okay, so this 2e 2e gets cancelled, and this is the equation of an ellipse. Okay, so if you want to plot its yield locus, that yield locus will be so it will look like an ellipse. Maybe my drawing should, I don't know how good it is. Hi, sorry, it made it as a circle by its own. But yeah, I mean, you get the idea, right? What I'm trying to do here is it should be an ellipse, and if you plot it using some software, etc., you'll get that. So this will be your sigma y minus sigma y minus sigma y sigma y, and this is your sigma 2 axis. Let's say this is your sigma 1 axis. So this will be your yield locus, and this will be your safe region. So this is your safe region, and this is yield locus is elliptical in shape. But the thing you should know that it is it is a function of mu. Okay, so mu is nothing but Poisson's ratio. So that dimensions of ellipse will change if mu is changed. Okay, and then what happens to this theory in terms of pure shear? In pure shear, sigma 1 is tau and sigma 2 is minus tau, and epsilon 1 is sigma 1 minus mu sigma 2 by E, so that will become 1 plus mu into tau by E, and sigma 2 epsilon 2 will be sigma 2 minus, so that will become again minus 1 plus mu into tau by E, right? Or if you want to just use this equation, you can do that also. So you put that there, so you will get tau square plus tau square minus 2 mu tau square less than or equal to sigma y square. And you can take tau out and then take a root on both the sides. You'll get 1 plus 2 plus 2 mu. Correct. 2 minus 2. It will be plus, no, because minus is already there, so this will be plus. Yeah, so we'll get 2 plus 2 mu. So if you put mu equal to 0.3, this comes out to be 0.62 sigma y. This is close to 0.57 sigma y practical value. Yeah, so this theory is good enough, like better enough for ductile materials also, not for brittle materials, because in any theory where you have strains and all those things, multiple stresses, etc., usually not used for brittle materials. Brittle materials only Rankine is good enough. Okay, and then the last theory, which is called as von Mises theory, which is very famous, and there are multiple names for this theory. You can call it as maximum shear strain energy theory. Shear strain energy theory, or it is also called as distortion theory, or it is also called as von Mises and Henke theory. But we typically use this von Mises or von Mises. Mises should be better, but okay. But this Henke guy is also there, but many people forget him. Okay, so this guy says that for safe or for no failure, the criteria it is given is maximum shear stress energy per unit volume should be less than or equal to shear strain energy per unit volume. So maximum shear strain energy per unit volume should be less than or equal to shear strain energy per unit volume, or you can call it as yield shear strain energy per unit volume. And now what do you do next is one second. Yeah, so Okay, so then yeah, there is again one derivation for this part. How do you calculate yield stress, yield shear strain energy per unit volume? And this part, this total shear strain energy per unit volume is calculated as volumetric or linear shear strain energy per unit volume. Yeah, this is maybe confusing, so I should write volumetric or, and then you add shear strain energy per unit volume. And sorry, you don't do that. You basically, yeah, this will be your total strain energy, per unit volume. This is I mean, this whole equation is used for calculating this part. This is what we need, right? So there is a derivation for all that. We'll not do that because we don't have time. And you know the final formula we already know. It is, if you do this thing, what do you get is sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square, sigma 3 minus sigma 1 square will be less than or equal to sigma y square, and there will be 1/2 here. Okay, and if you have like factor of safety, then this will be sigma y by factor of safety square. Okay, so what happens in 2D? Again, we need to plot this yield locus. So for that, sigma 3, let's say, is 0 because we are talking about 2D condition. So then this equation becomes, you'll have sigma 1 square plus sigma 2 square. That will become 2 and minus. So, that 2 gets cancelled from the outside and it will just becomes okay. And if you plot this, you'll get a curve. This is again an elliptical curve like this. So this will be your, let's say, sigma 1 axis, sigma 2 axis. This will be your sigma y minus sigma y minus sigma y plus sigma y. This is again ellipse, but the difference from previous case to this case is it is independent of mu. Okay. So now we have to check what happens in pure shear case, because for ductile materials that is the problem. So sigma 1 becomes tau, and let's say sigma 2 is then minus tau. In that case, you'll have tau square plus tau square minus tau square. But that minus minus will become plus. So this should be less than or equal to sigma y square. So therefore your tau, which is your principal stress, should be less than or equal to sigma y by root 3. And this is nothing but 0.577 sigma y. So therefore it is best suitable for ductile materials in pure shear case, because it is very close to the practical failure limit, that is 0.57. Okay. So these are like, some important these things, what do you say, theories and failure, and how to plot this yield locus, etc. And these are, I am saying again, these are like corresponding to your what do you say, elastic deformation limits. So you don't go into plastic deformation for these kind of failures. Okay, so for plastic failures, there are different type of things. Okay, and okay, so then apart from this, there was some discussion on octahedral stresses. Basically, octahedral stresses, if you join all the uh, planes that make equal angles with your xyz coordinates, then you get a octahedral shape. Okay, and it is important in some materials because there are some, depending on the packing structure, etc. You'll have certain important planes within the crystals, and all those things become important in those contexts. Then there is something called as effective stress, you know, and effective strain. So those things are discussed in the class, and you know, then after that, plastic deformation cases such as Lévy-Mess's equation, which is valid for only ideal plastic cases, and this Rundle-Ruiz, which is valid for elastic strain plus plastic strain. So that difference, if you remember, that will be better. And then towards the end of the class, there was some discussion on temperature change during the plastic deformation. So maybe I'll just give you or revise that formula. So, you know, yeah, this is the end of our failure theories discussion. So now let's talk about delta T, or temperature change during plastic deformation. So there are two cases here. One is, assuming frictionless deformation, and assuming deformation with friction. Okay, so if it is a frictionless case, you get delta T formula, which is your temperature rise, as average stress, or your plastic stress, average plastic strain. This beta is a factor which tells you how much energy went to the uh, plastic deformation out of total energy. Rho is density, C is as heat capacity, okay, or specific heat capacity if you want to call it. And in friction, you'll have a slightly different formula, because in case of friction, you need to consider certain things, such as this V is volume and this is velocity. Okay, these formulas are already given in the class, but I'm just telling that is a coefficient of friction. P is a pressure, so pressure at the frictional surfaces. If you take average, you'll get average delta T. If you take maximum, you'll get maximum. Those things. And AV is nothing but the volume of the material that is undergoing the deformation. The denominator V is total volume, so uh, that is there. And yeah, maybe you'll have some questions on this in your assignment also, so you can solve them. Just make sure you have you know proper units. Okay, so don't make mistakes in terms of units. Other than that, you'll be fine. Okay. So yeah, then then the discussion on this, what do you say, uh, hot forming and cold forming was there. So we'll discuss about them briefly and then we'll stop for the day. So, you know, again, when you say hot forming and cold forming, or in general in the context of hot and cold, it is always with respect to some reference. Okay, so whenever you say something is hot and cold, it is always in terms of some references. So here the reference temperature is basically your what do you call recrystallization temperature, and then in that context use this term hot and cold. Okay, so you know, so if you are operating at temperatures higher than your, I think the recrystallization temperature, okay, 1 second, recrystallization temperature usually, it is like 0.4 to 0.5 times the melting point, and that too in Kelvin scale. Okay, so please keep that in mind. Don't take degree Celsius in the formula, otherwise you'll get a wrong answer. Okay, so then if you are operating above your recrystallization temperature, then that becomes hot working. This will be when your temperature of working is greater than recrystallization temperature, and cold working will be when you will have the operating temperature during your uh, forming process or working process than the recrystallization temperature. This is the basic criterion. Now, then there are some pros and cons of hot working and cold working, etc. So I'll verbally tell them because those things are already discussed in the class, and slides are already there, and you can Google it also. But there are certain important things about them that you should know, and we'll talk about those. So hot working. So you should know when to use which method. So it all depends on what do you expect in your end product after working or after metal forming process. So hot working is used uh, for large deformation rates. Okay, so if you are deforming materials for a large rate, and what I mean is, let's say if you are wire drawing and if you are stretching some wire from a metal pool, then if it is hot, then the if it is above recrystallization temperature, then the fluidity will be better. It will be easy to stretch that wire out of that. So you can have large deformation rates in this case, and your flow stress typically remains constant. So you need not to increase your flow stress as you do the working. Okay, but you know, and yeah, since you have recrystallization, you'll have lesser uh, defects or inhomogeneities or defects. Okay, because you are operating at higher temperatures, and those defects are because your grain structures and sizes will get readjusted. Therefore, the defects won't be that significant. There can be some defect. It's not like defects won't be there, but yeah, it will be lesser. And second thing is you'll get a smaller equiaxed recrystallized grains. Okay, so these are some advantages of hot working. So let's say these are some pros. What are some cons of hard working? Hot working. not hard working. Okay. Yeah. So what happens? Sometimes uh, you know you need inert environment. Otherwise, there will be formation of oxides or any other byproducts. Then you lose your useful material to the byproducts, etc. So usually, inert environment is required for that, and uh, higher maintenance, because uh, first of all you need to make sure that safety is ensured because you're operating at higher temperatures, and apart from spending energy for that higher temperature achievement, you have to be careful that if any oxide is formed, that should be scraped off before the next pass, otherwise the next pass will get contaminated, etc. And what happens, uh, see, you have to be careful, because if you want equiaxed grains, you have to maintain certain cooling rate. If you don't maintain that, what happens, these smaller grains will become coarse grains if proper cooling rate is not maintained. And as we all know, when you have a larger grain size, your strength goes down. So sometimes what happens, even after doing the hot working, you have to be very careful about the temperature of the material at the last pass. Okay, so if it is not proper, because usually if you don't actively cool it, then you have to be careful as to how much cooling rate by the ambient will be achieved after last pass. So those things are very important. If you don't pay attention to those, you'll the desired properties will be not achieved. You'll get lesser strength. And as the name suggests, uh, you know, here what happens, you operate below the recrystallization temperature. So you cannot go for higher deformation rates. So because otherwise your material will fail in the plastic deformation case, because it's the there is no uh, temperature or higher temperature that will absorb that deformation. Here the grain sizes are reshaped because of only the forming or the working pressure. Okay, so therefore you'll have lesser deformation rates. That is one. And uh, but you'll have higher uh, increase in the strength because of cold working. Yeah, that is understandable, right? Because that is the main point of doing cold working, that because of strain hardening, etc., you'll get higher strength out of it. Okay, and you get basically columnar grains after cold working. Okay, because you'll not have that uh, what do you say, the luxury of higher temperatures, and therefore your grains will be columnar. Okay, so I should not say columnar, I should say elongated. Elongated is the correct word. Elongated. Okay. And uh, these are the advantages. What are the disadvantages? The disadvantages is uh, higher flow stress. So basically, you need to supply the or you need to provide higher stress during forming or working, cold working, and it may vary with respect to the amount of material left, or what is the deformation, at the start or at the end. So that is not a constant flow stress. Okay, so it is a variable as well as higher flow stress. And you don't have that inert environment requirement here, because you are below the recrystallization temperatures, and you don't have non-desired byproducts or chemical reactions. So maintenance is lesser, but again, you know you'll have more defects or more residual stresses in your component if you do cold working, because the grains are elongated, and they don't have chance to release those stresses because of this shape deformation, etc. So that leads to more defects. Okay. And what typically done is, you know as always in the most cases in life also, if one thing is better than the other in some manner, and the other thing is better than the first in some other manner, we try to find the common ground. So here also what typically done is, usually cold working is done, and then you do annealing. So basically you get best of both worlds. First of all, you don't need to go for higher recrystallization or higher operating temperatures, and you can you know operate at lower temperatures. You can achieve your cold working in one pass, let's say whatever step deformation rate you wanted. Then you anneal that product. So basically you uh, relieve the stresses between, and you maintain certain cooling rate so that you get the desired output. And after annealing, then again, if you want more deformation rates, again you make one pass more. So again that material will be again cold worked, and then again also it will be annealed. So this is like the best case scenario. So if you are worried about always good that after cold working you do the annealing. So the problem is, if you do cold working plus annealing, you will pay more cost as compared to cold working. But then you have to decide the trade-off. With if you are okay with the defected or higher residual stresses end components, then no need of annealing. But that is important for your end application. If your end application does not, or it is very critical that there should not be any residual stresses, so in that case, you have to do annealing after cold working. So the cost will increase, but again, other things are also into the picture. Okay, so this is how you do cold working and hot working. We'll talk about these things later also in the next week discussion, because we'll discuss something about rolling in the next week, then forging, etc. So these things, hot working and cold working, will again come into different contexts. For example, hot rolling, cold rolling, hot forming, cold forming, hot extrusion, cold extrusion. So these things we'll see again and again. So don't worry, we'll discuss them. So, but this is like a general hot working and cold working discussion. And yeah, hopefully you understood what I'm trying to convey. And with that, we'll stop for the today's class. And yeah, uh, because we're almost towards the end of the class, and then we'll meet next week and we'll discuss the next things. So basically, we started these forming processes from week 5, metal forming as a chapter, but till this lecture mostly we have discussed about the strength of material aspect of this, because for forming it becomes very important to understand when it will fail or not, because if you don't understand the failure things, you cannot successfully do forming. For example, if you don't know the plastic stress strain equations, like those Trovis, etc. When you are doing cold working, if you don't take care of those maximum stress values, etc., you will be encountering fractures or cracks or something like that, and then again your efficiency or productivity goes down. So you have to be careful, and that's why we discuss so much this theory behind this before starting actual forming discussions. But from next class, I think the discussion will be more focused on the actual metal forming practical processes. So yeah, that is the broad idea. So let's meet on next class and we'll discuss more then. Okay. So we'll stop for the day now.